Let's talk about your own research career. You've spent quite a bit of time understanding multi-phase natural phenomena, volcanic eruptions, avalanches. Tell us a little bit about uh, what we learn using CFD from a problem like that we couldn't just learn from visual observations.
True. It's again a great question. So, especially the kind of problems I was dealing with are problems CFD plays a unique role. Okay, let me just give you a few examples. Let's think of a volcanic eruption, and you want to know some volcano you know that might explode, and you want to know what kind of consequences, how you're going to redirect your air traffic and things like that. It's not like you can do an experiment. I mean, it is what it is. And then also, when it happens very fast. Same thing with powder snow avalanche, dust storms, um, or how coastlines erode over time. These are on scales that you cannot run an experiment. Mantle convection is another problem, actually. You just can't do experiment or astrophysics, okay? So there are a lot of problems where CFD is the only way you can learn what happened in the past, what could happen. Okay. The other problem that we did was from an engineering side, we wanted to study why Titan rocket blew up or Challenger disaster. Okay. This is like a hindcasting. Okay. There, you can't run an experiment again. You just have to sort of use simulations to find what could have happened. Another one, security things. For example, you want to know how a truck bomb may impact some very sensitive government building. You can't do experiments on those kind of stuff. So CFD is a must in a variety of problems, even because you just can't do experiments. There is no other way but to study those problems using computers. But that's not where it stops. There are other problems. Say, for example, you're designing a new nuclear power plant or a five-stage rocket. Each experimental run could be billions of dollars. So
Mhm.
there are many different reasons why CFD has become a very important tool.